Good evening, everyone. Welcome to week 6 problem solving sessions for the course on data science with R. I am Shreya, one of the TAs for this course, and today I'll be discussing concepts discussed during week 6 lectures and some related problems. I hope these will help you a bit in solving the assignment questions and also learn. So let's get started. All right. So during week 5, in week 5 we learned about just a minute. Yes. So in week 5 we mostly learned about confidence intervals. Okay. So what is confidence interval? So if let's say I have a population parameter, let's say I'm interested in the parameter mean. Okay, so I would want something like this, that a less than equal to b less than mu less than equal to b equal to 0.95. So then I would say mu is contained in this interval with probability 95%, and these would be the upper and lower bound of a confidence interval. So this falls under the purview of interval estimation. And why do we do that? Instead of giving a single point estimate, we provide a range, and not only that, we also say how confident are we with the range that we provide. So if I have a very small confidence interval, that is actually desirable. So this is broad and this is narrow, and this one would be preferred or desired for several reasons, which I'm not going into now. Okay, so we learned about how to formulate confidence intervals for mean. In this case, I should write population mean when samples are drawn from or are drawn with SRS, both WR and WOR. Okay, so this is what we learnt in week 5. Now, those samples were majorly continuous variables. So during week 5 we learnt y1, y2 and yn These are majorly these could be continuous variables or some categories. Okay, something we did not explicitly talk about categories. We are going to do it here. So we mostly, whenever we were talking in the last few weeks, we mentioned some population characteristic which was denoted by capital Y, and that was done without saying how Y looks like, but inherently we assume that all Y's will be continuous, but we are going to expand the usage and see what happens if all Y's are not only continuous but also if they, what happens if we have indicator variables. Or indicator variables would mean yi equal to 1 if something, for ith individual, or 0 if something else for that particular individual. So this week we are going to discuss what will happen when we have a sequence of 0 and 1s in the population. Okay, we'll have indices. So this will be individual 1, this will be individual 2, and this will be individual 3 or n, let's say. Okay, so now the problem translates to, if in this sample I want to know how many ones are there, like that would give me the total count. So summation yi I equal to 1 to n would give me the total count of some cases, let's say, which are denoted by constituent yi equal to 1. And if we take the mean, population mean, this population mean is actually nothing but population proportion. So this week we are going to see how the results translate when we are talking about population proportions instead of the inherently assumed continuous y. Okay, so how do we do that? But before moving on, I am going to reintroduce some terms which will help in understanding the problem. Okay, so we are going to define, let's say this is my population and I have y1, y2 to yn. This is the population. Okay, oh, I've written population, so I'll just, so let this be called as setup. Okay, and from here we draw a sample of size small n, and we have, this is our sample. Okay, then population proportion, also let us define yi equal to 1. If it's a case, this case definition will vary from problem to problem, and 0 if not. So then population proportion 1 by n summation I equal to 1 to n yi. Summation yi equal to 1 to n is actually population count or rather count of cases, and if we divide the count of cases with the total number of individuals, we get the population proportion. Okay, so this one we'll call as capital P, actually the y bar in our study. Okay, now if I want to define sigma square, that is the population variance, I should write 1 by n summation I equal to 1 to n yi minus capital Y bar whole square. So if we expand this, we'll get 1 by n summation yi square, okay, I equal to 1 to n minus 2 y bar summation I equal to 1 to n yi plus summation I equal to 1 to n y bar whole square. So this then becomes 1 by n summation I equal to 1 to n yi square minus 2 this part summation capital yi will be n y bar and we already had a y bar here, so that would become square, and here we'll have plus y bar square is a scalar, is not dependent on the on the sum term, it's a constant, or in other words y bar square is added up n times, so that would mean plus n y bar square, so this would be 1 by n summation I equal to 1 to n yi square minus n y bar square. Okay, so yi's are 1s or 0s, so yi square will also be 1 or 0, and summation over I equal to n yi will give me the number of cases. Okay, so let me denote this by C by n, and this will be also be, and y bar is nothing but P, the population proportion, so this will be np square. So this would actually be C by n will be P minus n p square. Okay, so sorry, I think I did some mistake over here. So what I'm trying to do is I'm trying to set up the population proportion problem. Here I have capital Y1 to capital Yn that represent the population values. From there I am drawing a sample of size small n. So I would have small y1 to small yn, and yi's are such that yi's are 1 if it's a case, okay, some sort of some characteristics, let's say, and 0 if not, okay. So population proportion in that case will be 1 by capital N summation I equal to 1 to n yi, okay, and that would be equal to capital P, or that is capital Y bar. Sigma square in that case would be 1 by n summation yi minus y bar whole square, okay. So this would be 1 by n summation yi square minus 2 y bar into summation yi plus summation y bar square. So summation yi is again n y bar, and this is y bar square summed up n times. So minus 2 n y bar square plus n y bar square would give me this, okay. Okay, so here I would have summation I equal to 1 to n capital yi square would be the number of cases by n minus n will cancel, y bar square is population proportion p square. So we are going to have p minus p square, this p into 1 minus p, we call this as q, okay. So sigma square is actually p into q. Now how about s square? This is nothing but similar to sigma square with denominator, 1 by capital N minus 1. Summation I equal to 1 to n capital yi minus y bar whole square. So this, if we again expand, will be 1 by n minus 1 summation I equal to 1 to n yi square minus n y bar square. So this one is 1 by n minus 1 n into p, because it gives the number of cases, minus n p square. So this would be n p 1 minus p by n minus 1. So this is actually capital N by n minus 1 p q. So now we are going to derive the sample counterparts of these expressions. So let me do that. So here I have small s square, which would actually estimate by capital S square. So small s square is what? It's the same thing as capital S square, but the sample version of it. So it would be 1 by small n minus 1 summation I equal to 1 to n small yi minus small y bar whole square. Okay, so we'll again expand 1 by n minus 1 summation I equal to 1 to n yi square minus n y bar square. So summation yi in the sample would be total count of ones in the sample. Okay, so that would actually be 1 by n minus 1 n into small p, okay, minus n into y bar is also small p. So this would be small p square. So this would be n by n minus 1 small p small q. Okay, so this is there. Now, having said these, what are we essentially doing? We have a pool of y1 to yn, which could be ones or zeros. Okay, we are also sampling a set of 1 or zeros, and then we are calculating what is the population mean. So this is population mean. Or rather I would call this as proportion in present case. And here we have the small p, which is the sample mean in present case. So we have seen that y bar unbiasedly estimates y bar. Okay, for SRS we have seen this. So naturally, in case of proportions, small p will unbiasedly estimate capital Y, unbiasedly estimate capital Y bar, which is nothing but the population proportion. Okay, now we have obtained the estimate of population mean, but how good that estimate is, we'll be able to tell by looking at some other metrics, which there could be a couple of things that you can check. Typically what we do, we check the standard error, okay, and that would be variance of the estimator, like variance of the estimated variance of the estimator and square root of that. So that would be the standard error. Okay, now let's see what happens in this case. So since small y bar unbiasedly estimates capital Y bar, by similarity or by extension, small p, because that is also sample mean, is unbiasedly estimating the population mean, that is Y bar or capital P. Now let us find out what is the variance of this y bar under different schemes. So variance of y bar WOR we have known for SRS, that is n minus n by capital N capital S square. Okay, now S square we have seen here, capital S square is nothing but capital N by n minus 1 PQ. So if we replace that here, so we'll have n minus n by n into n by n minus 1 PQ. So this would actually give me capital N minus small n, capital N minus 1 PQ by small n. But what happens if we go for with replacement sampling scheme? That is equal to n minus 1 by n capital S square. So that would be n minus 1 by capital N small n. We'll replace it by capital S square value, that is capital N by capital N minus 1 PQ. So this would be, where is it? PQ. Okay, so n minus 1 here will cancel, and n will also cancel, so we'll be left with PQ by n. Now mind you, P and Q are population parameters and they are unknown. So what do we have to do? We have to use the sample form. Okay, so if we say that we want variance of y bar WOR, but we want the estimated variance, so this is actually called as hat sign and gives the and indicates rather that we are calculating the variance so this is hat sign will say that this is actually an estimate. So what we are going to do, we are actually going to replace these capital P and capital Q by small p and small q. Okay, because why? This is n minus 1 n capital S square, so this would be n minus 1 by n. Instead of capital S square, I would have small s square. Okay, so here if we expand, we'll also get similar terms in terms of, sorry, this shouldn't be n minus 1. We should have capital N minus n by nn small s square. So this is capital N minus n by nn summation I equal to 1 by n minus 1 summation I equal to 1 to n yi minus y bar whole square. So this would be n minus n by nn 1 by n minus 1 summation yi square is n p minus n by n minus 1 p square. Now this is how you would calculate v hat y bar WOR, but question would arise that, you know, why is it that I would calculate, I should replace s square by s square and not, because since I have this one PQ, and since we know that expectation of small p equal to capital P, expectation of small q equal to capital Q, why not replace capital P by capital P and small q by small q? Well, I did this mistake. Why I call it a mistake is because, see, expectation of P equal to capital P, this is true. Expectation of Q equal to capital Q is, this is true. But expectation of PQ is not equal to P into Q. So we shouldn't use or replace capital P and capital Q by small p and small q. Alright. Individually, expectation of P equal to P, expectation of Q equal to Q. Okay. Expectation of small p equal to capital P and expectation of small q equal to capital Q. But expectation of small p into small q is not equal to PQ. So hence we have to calculate from scratch. Okay, so this entire thing is wrong. So then what is the correct thing to do? It's here. So variance of y bar WOR is actually capital N minus n by nn capital S square. Now we know expectation of small s square equal to capital S square. So therefore variance of y bar WOR hat will be n minus n by capital NN into small s square. And how does that look like? That would be n minus n by capital N into small n, small s square. So that would be 1 by n minus 1 summation I equal to 1 to small n yi minus y bar whole square. So this will be capital N minus n by capital NN 1 by n minus 1 summation yi square minus n y bar square. So this thing is P and this is also P. So we'll have n minus n by capital N n, 1 by n minus 1, n into P minus np square. So this would be, n would cancel, we would have n minus n by capital N into small n minus 1, P into Q. Is it okay? So this would be n minus n by capital N, n minus 1, P into Q. Similarly, we have this formula which is true. These are population parameters. But this thing, variance of y hat WR P cubic by N, this again is wrong. Consequently, this also is also wrong. Okay. This is true, but expectation of PQ not equal to PQ. Okay. So what is the correct thing to do then? Then same thing, V hat y bar WR is actually equal to n minus 1 by nn small s square. That would be n minus 1 by nn 1 by n summation yi square minus y bar square. So this will be minus n1 y bar square. So this was have 1 by n minus 1 into 1 by n np minus np square and this n would cancel, so we would have okay, so this is small s square. Another thing, small s square should come with a small n minus 1. So that should be npq by n minus 1 So variance hat y bar wr would be actually s square by n. Okay, we have seen this previously, and s square is n by n into n minus 1 pq. So this actually turns out to be pq by n minus 1. Okay. All right. Now once we have this, all of this was with regard to population proportion. Now what is going to happen if we have population total? Like let's say you are conducting you have launched a new product in the market, and you want to know how, I mean, instead of the question being what proportion of people are actually using or are likely to use the product, you want to know the let's say the total count, because you could have varied interests in mind. Suppose you are working in a production, and then you have launched a test software of sorts, or it could be any test product, and you distributed it. Okay, and then you distributed it to the sample, and then you want to scale it up. All right, and based on how many users in your sample used it, you want to estimate how many total amounts you need to actually manufacture or produce. Okay, so you need that number because you want to scale up your business, or any, it could be anything, so that it reaches the target population that you have in mind, and you need to know how many you should manufacture, so that there's no shortage. Now this problem is not as simple as it might be sounding right now, but I think you get the point where I'm coming from, that not only are you interested in proportions but also totals. So now we are interested in the total estimation. So in that case, we want a total estimate of C. Let's say C denote total cases or counts in the population. All right. So C is actually equal to capital N into capital P. Okay, but C hat is actually an estimate, so that would be capital N into small p. Okay, so then variance of C hat is actually capital N square into variance of P. Okay, so what this means is that, let's say I have YWR, that is 1 by n, not 1 by n, that is summation yi, and y hat WR will be n into p, and variance of y hat WR will be n square into variance of p, which is nothing but variance of p is what? PQ by capital N. So this was n square into PQ by small n, sorry. And variance hat of y hat WR will actually be n square into variance hat of P, and that is PQ by n square into PQ by n minus 1. Alright, similarly, so this is y total so this is total counts in with replacement scenario. What happens if we look at total counts without replacement? This one without replacement is the same, I equal to 1 to capital N yi. Y hat WOR is actually capital N into small p. Variance of y hat WOR equal to variance of capital N into small p, which is equal to variance of, or rather n square, variance of small p, which is n square into n minus n by n minus n by n minus 1 PQ by small n, and V hat y hat WOR is actually n minus n capital N square into n minus n PQ by capital N into small n minus 1. Okay, so this will be n into n minus n PQ by small n minus 1. Okay, so once we have this, if somebody asks what is the standard error, that would be root over b hat y hat wr, that is root over of this quantity. Okay, inside you would have this quantity. Same goes for here. If somebody asks what is the standard error, root over of this quantity. Okay, similarly, if we had asked for standard error, it would be root over pq by n minus 1. Okay, and similarly, if anybody would have asked, then here standard error equal to root over n minus n by n into n minus 1 small p into small q. Okay, so if I have to collate everything together, let me just write it down so that it's easier. So I'll make 4 subsections. One will be proportion y bar and one will be total. Or p, and one will be total y. Okay, so y bar hat is actually small p. Variance of y bar hat equal to n minus n by n minus 1 pq by n when we have WOR, and pq by n when we have WR. And variance hat y bar hat is equal to pq by n minus 1 when sampling with replacement, and n minus n by capital N into small n minus 1 if we have into small p small q if we have WOR. Okay, and y total is actually n into small p. Variance of y total is equal to n square into n minus n by n minus 1 pq by n when we have WOR, and n square pq by n when we have WR, and v hat y hat is actually n into n minus n by small n minus 1 pq if WOR, and capital N square pq by small n minus 1 if it is WR. Okay, and standard error would be root over v hat y bar hat in this case, and this would be standard error would be root over v hat y hat in this case. Okay, now once we have the means and variances, how do we frame the confidence interval? The confidence interval would be small p minus z alpha by 2 root over of variance of p and we should add p plus z alpha by 2 root over variance of p. Now mind you, we are not writing variance hat of p over here because variance of p will also so it should have variance of p hat, okay, because that is what we are specifying. Okay, now this is under the assumption that n and n are large, and then we assume p minus capital P by root over variance at p to follow a normal 0, 1. Strictly speaking, we assume this to hold. Okay, not the hat ones, normally. So once this is done, confidence interval and all, let me just move on but before that we can also use some adjustments to this exact existing confidence interval. Since this is a discrete random variable 0, 1, 0, 1, we could make some approximation. So for that we'll have some adjustment related terms over here, like plus n by 2 and minus n by 2. So these are actually typically the adjustments that we are trying to make. Alright, so we'll keep this formula in mind and then look at how to do things in R. Okay, so here we would have to do some sort of selection. Okay, proportion and percentages. Suppose we have capital Y as a sequence of variables, let's say a true false sequence, or it could be anything. Let's say that if ith person, my question is, do you own a house? Okay, so I am going to generate 20 10 values, 1 0 0. This is completely random. Okay, whatever. So how many do I have here? If my Y is this, I have 16, so I'm going to add 2 more. Okay, so let's say capital N is 20. Oh, we have 18 only. Oh, let's say, yeah, that should be it. So we have 20 elements, right? Let us save this as week 6. So now the issue is, even if we do SRSWR or SRSWOR, just by looking at the result, we won't be able to understand whether WR or WR. In that case, we should exercise caution and read the question. Whatever the question says, that is going to guide you which formula to use. Okay, so let's say I want SRSWR. So I'm going to do sample WR equal to sample capital Y. Let me sample a sample of size 8, let's say. So I'm going to write size equal to 8, replace equal to true, and I'll set a seed. so that I get the same answer every time this is run. So I save it as 1 2 3 4, and I also draw another sample, but that should be WOR. So here replace equal to false. So I'm going to run this together. Okay, so from the samples you can see that it's fairly impossible to distinguish which has come from which sample. I mean, there's obviously a way to do that, but just by looking at the sample like this, we won't be able to tell. So, but how can we say whether this has come or not? If we, instead of sampling the Y values, if we sample the individual IDs and then work with the raw values, only then we'll be able to say. But anyway, just by using this on the raw indicator variable column, we won't be able to tell. Okay, so now we have our samples. So let's say PWR is actually sample mean. So mean of sample WR. So that is 0.75. PWOR is mean of sample WOR. That is 0.5. Okay. Variance WOR is how much? Now we'll have to go back to this formula. So variance of WOR is n minus n by capital N into n minus 1 PQ. Okay, so that would be, so here n we have this small n equal to 8. So this will be n minus n by capital N into n minus 1 into PWOR into 1 minus PWR. So let's see how much is it coming. So this is 0.214. Now just to cross check, is it the same thing if we just replace it with this? If we just do n minus n, capital N minus n by n into n into variance of, because you remember variance of I is actually the S square. So variance of sample WOR. If this is the same, yes. So we have derived our expressions correctly. Okay, this is exactly the same. Similarly, for VWR, this is PQ by n minus 1. So this into this by small n minus 1. And if I am doing this as variance of PWR, okay, so this will be WR, not WOR. So this will be P variance of WR S square by n, small n. So let's see if these match or not. variance of sample WR. So this one is actually 0.026 and this one is also exactly the same. So we have derived our formulas correctly. Alright, now if I just want a total, so V var total will be how much? Will be n square into V var okay, or and V var WR total would be same thing, capital N square into variance of WR. Okay, in any case you will see the without replacement variance is lower than the with replacement ones. Is it okay? Right. So now let us just briefly touch upon some parts of the stratified sampling, whatever we learned. Okay, so right now what we were doing, we had a pool like this population where each element had probability of selection equal 1 by n. Okay, but in SRS what was happening, we selected something, we gave it back and then again reselected WR. But in SRS WOR what had happened, we were selecting and then we were keeping. So at each iteration, probability of selection of an item would remain equal. So probability of selection of an item at first glance would be 1 by n, then it would be 1 by n minus 1 and so on. So anyway, what we were doing, we were actually sampling randomly from a pool. But now if say this population has subclasses, this is let's say class A, this is let's say class B, this again let's say is some class C. Okay, and there are inherent differences in between these classes. So when that happens, we cannot just take an overall sample. Okay, so if it so happens that we take NA samples from here, NB samples from here, NC samples from here to make our sample, then this sort of an approach is actually called as stratified okay, we are selecting randomly with SRS from each of the strata. Now what that implies is this. So if we have actually 1, 2 to n units, strata 1 would have 1, 2 to n1 units, strata 2 would have 1, 2 to n2 units, strata P would have 1, 2 to np units. And then from here we select n1, from here we select n2, from here we select np, and all of these add up to n. And this selection, all of this is done by simple random sampling. So this is actually the setup. So in this case, let's say I have these boxes which are my strata. So this one has n1, n2, n3, n4, and I want to estimate capital Y whole. So that would imply 1 by n summation I equal to 1 to n I yi bar. Okay, this is a SRS sample, so I have yi bar. From here also I have some yi bar. Here I have y3 bar, here I have y4 bar. But I'll be able to estimate with the help of the sample means in each of these strata, because within the stratum we are doing simple random sampling. So for stratified sampling, this actually is the y bar under consideration that we are trying to estimate. And how are we doing it? What is the estimate? This estimate is nothing but 1 by n summation I equal to 1 to n ni yi bar. But mind you, this one, is it unbiased? Let us find out. So if we do this, if we take this as the equivalent sample form, then expectation of y bar hat is equal to 1 by n summation I equal to 1 to n ni into expectation of yi bar. So this will be 1 by n summation I equal to 1 to n small ni into yi bar. But this is not equal to 1 by n summation I equal to 1 to n capital Ni yi bar, which is equal to y bar. So this measure is not unbiased but biased. This is of course an estimate, but this is not unbiased. So what is the bias if we want to calculate? So bias is expectation of y bar hat minus y bar. So we had that expectation of y bar hat, that is 1 by n summation I equal to 1 to n ni yi bar minus 1 by n summation ni yi bar I equal to 1 to capital N. Okay, whatever this term comes out, that is actually the bias in the data point. Now what happens if I change this to 1 by capital N summation I equal to 1 to capital Ni small yi bar. Then expectation of yi bar is equal to 1 by n summation I equal to 1 to n capital Ni expectation of yi bar small yi bar, that would be equal to 1 by capital N summation I equal to 1 to n capital Ni capital yi bars, but this is equal to y bar. So then this one is actually unbiased. What happens if we change the estimate to 1 by n or let's say 1 by n summation I equal to 1 to or rather let's say 1 by n summation I equal to 1 to small n small ni yi bar. In that case expectation of y hat bar will be 1 by n capital N summation I equal to 1 to small n ni expectation of yi bar will be capital yi bar. But this is also not equal to y bar. So the bias would be expectation of y hat minus y bar. So if you subtract y bar from this, whatever result you would get, that would be the bias in your study. All right. Okay. So this is how you would get an unbiased estimator of the population mean. And if you want, so this one you will call as y bar st and variance of each stratum mean would be variance of y bar, let us call this as stratified. This is equal to, so we are going to prefer unbiased estimators always. So the one that was unbiased was, let that be y bar st. So it was 1 by n summation I equal to 1 to I should write, not write n here, I should write 1 to k because I have k stratas ni yi bar. Let me make this modification. So here I have k groups, let's say. Okay, I think I've made all the corrections. No, here it will not be capital N, it would be capital K. Here also it will be capital K. Let us say we have K stratas. All right. So variance of y bar st, once we have established what y bar st is, so here we can also write it as I equal to 1 to k ni by n yi bar. So that could be I equal to 1 to k wi yi bar. So this wi is actually ni by capital N. So variance of y bar st is actually summation of yi square variance of yi bar plus double summation covariance between yi yj into wi wj. Okay, so this will be I not equal to j and this is I equal to k. Okay, now since covariance of yi bar and yj bar will be 0 since samples are drawn independently from groups I and j. Whatever strata from which I am selecting the sample, it doesn't depend on whatever I have selected in some other strata. It's completely random. So that is why these covariance terms will disappear and we would have variance of y bar st equal to summation I equal to 1 to k wi square variance of yi bar. Okay, and that would also remain same in the sense that this would correspond to the individual group level things. Okay, so this will happen summation wi square I equal to 1 to n capital Ni minus Ni by Ni into Ni Si square if WOR and summation wi square I equal to 1 to k this would be Ni minus 1 by Ni Si square if WR okay, and similarly we would have SI square, small SI square in place of. So here if I want to have the V hat y bar st, that would be summation I equal to 1 to k wi square variance hat of y I bar. So this would be summation I equal to 1 to k yi square this would be ni minus ni by ni s I square if it is SRSWOR, whereas this will be summation I equal to 1 to k yi square si square by ni if it is SRSWR. Okay, and in any case standard error will be root over this thing, root over these here represented here. Okay, now from this equation we can see, so strata should be such that within strata it should be homogeneous as possible, and between strata there should be as much as of a difference as possible. So SI square is actually computing within each strata how much of variation is there. So the lower that would be, better we would have the population as a stratified one. Okay, so again if this holds, then we would have the confidence interval as y bar st plus minus t distribution alpha by 2, and the degrees of freedom we have to compute divided by variance hat y bar st. And the distribution of this is a little bit complicated, so we haven't touched upon this part yet. Okay, so this was all about stratified sampling. Okay, and this is done because this would ensure representation among different sectors of the population, and this would also help us give us estimates very strata specific, or it will give us strata specific estimates as well. Okay, and there are also a couple of advantages to using this stratification. It could be administrative advantage, it could be some specific question that we have in mind with respect to different groups that we want to address. So all of these will be taken care of if we perform a stratified sampling. All right, so that was all I had for today. Thank you so much for listening.